So today we've been asked to convert a rectangular equation into polar coordinates and then graph it. And I'm going to show you how to graph this on your TI-83 or TI-84 graphing calculator. But the first step is to convert this to polar coordinates. Now, in a previous video, I gave you a formula that you can use, and we developed this formula using right triangle. And what we said was, and I'll go ahead and write it down for you, x is always going to be r cosine of theta, and y is always going to be r sine theta. Okay, so we're going to use those two equations to turn this into polar coordinates. Now, the goal of a polar coordinate equation is always going to be, if you look at your graphing calculator, typically you've got y equals blah. You always want y by itself, and you want the independent variable x on the right-hand side in multiple forms. Now, for polar coordinates, instead of having y in terms of x, you're going to have r in terms of theta. So it's going to be r blah, blah, blah theta. Okay? Now, 2y minus 3x equals 8. And we want to turn this into a polar coordinate equation. Okay, fine. Well, real simple. Everywhere you have x, substitute r cosine theta. Everywhere you have y, substitute r sine theta. And the x's and the y's go away, and you're left with everything in terms of r and theta. Then comes the hard part. Get r by itself on the left-hand side. And there's your polar equation. So, I'm going to say 2 times r sine theta minus 3 r cosine theta equals 8. Okay? Seems simple enough to me. Then we're going to distribute, so we will get 2 r sine theta minus 3r cosine theta equals 8. Also seems pretty simple to me. And my goal is to get r by itself. And I realize I have an r in both of these terms. So I'm going to factor that r out. And if I factor that r out, I'm going to end up with r times 2 sine theta minus 3 cosine theta equals 8. Okay? Now, I want to get r by itself. Well, the easiest way to do that is to divide. So if I divide, I'm going to end up with r equals 8 over, let me extend that a bit because I'm going to need it, 2 sine theta minus 3 cosine theta. And that is that equation in a polar form. Okay, so that is the rectangular equation. That is the polar equation. Now, what I like to do is just show people that this stuff works. Because, I mean, I can sit here all day and write stuff and tell you, look, this works. Trust me, don't worry about it. But I want you to see it for yourselves. So, one of the things I like to do is I like to take this equation right here. Use just a different color ink now. Take this rectangular equation. I'm going to put this in slope-intercept form, which is y equals 3/2 x plus 4. Okay? Y equals 3/2 x plus 4. That's rectangular form. And this is polar form. Okay? And I want to graph the two of these equations and see if they look the same. So, I'm going to pull out my handy-dandy graphing calculator here. And I'm going to go to my y equals screen. I'm going to just set this down here and zoom in a little bit. So I'm going to go, before we do that, I want to talk about this for a second. We go to mode. And if you go to mode, I'm going to zoom in a little bit more. You're going to see 4 modes here that are really important. In this particular example, we're going to use 2 of these. Okay, the default for your calculator is FUNC. That is function mode, And that means this is set up to graph functions, everything that passes the vertical line test. That is a function by definition. Okay. Another mode here, PAR, is parametric equations. And I may do a video on those later, but haven't yet. And then POL, which is polar equations. Okay. So if you have it in function mode, which I do, and you hit your handy Y equals key, here's what you see. Y1, Y2, Y3, Y4. So I'm going to type that equation. 3/2 x plus 4. Okay, so 3 over 2x plus 4. There's that equation typed on this calculator. And I'm going to hit graph. And I see a straight line. And specifically, I want you to pay attention to the fact that this line goes through 4 on the x-axis. And it pretty much, not quite, but I think it goes through really close to -3 on the x-axis. Okay, so there's this line graphed in rectangular coordinates. Okay, and if you don't know how to do that, you should see a video that I did earlier on that. Now, what I'm looking for is if I graph this thing in polar coordinates. Okay, if I graph this same line in polar coordinates, I want this graph to look the same. So I want it to cross at 4. And I want it to cross basically at -3 on the x-axis, just a hair to the right of that. So it's okay, what do we need to do? Well, the first thing is, to graph this equation in polar form, I have to change modes. So I click mode, and I scroll down, and I change to polar mode. Now I'm going to hit Y equals, and instead of Y1, Y2, Y3, what do we see? R1, R2, R3. This calculator is set up so that when you put it in polar mode, it expects an equation that says R equals blah in terms of theta. Now, so I'm going to type this equation, 8 divided by, and I'll put my parentheses here. Now, very, very important. You should always, always, always use this key when you are creating a variable. And it says xt theta n. Theta has to be the independent variable in a polar equation. And when I hit this key before, it made an X. When I hit this key in polar form, look what it makes. It makes the theta symbol. Okay, so now I need to type in my equation using that key. So 8 divided by 2 sine theta. Now notice my calculator opened a parentheses. I have to close that parentheses. Minus 3 cosine theta. My calculator opened that parentheses and I've got to close it. And then I opened this parentheses and so I've got to close it. And so this equation is this equation right here. And when I press the graph button, I see a straight line. And that straight line crosses at 4 here and it crosses basically at -3 here. Looks like the same line. And so that's kind of neat to see that even though this is a completely different form, that it makes the same line. The one thing I do want to mention is in polar coordinates, if you go to your window, normally when you look at your window in rectangular coordinates, it's X minimum and Y minimum, so that's the width of the screen. Y minimum and Y maximum, that's the height of the screen. But you notice an extra, so you still see X min is -10, X max is 10, Y min is -10, Y max is 10. That's our standard window. But then you notice theta min, theta max, and theta step. What in the world does that mean? Well, what we're doing, remember, we're talking about R, a distance from the origin, and theta, a rotation. And typically the smartest thing to do, I keep my calculator in radians pretty much all the time, is to make a complete rotation. Well, a complete rotation will be from 0 to 2 pi. So 0 to 6.28. And then theta step is basically how far apart do you want the theta increments when this thing's plotting points. And I've shown this in another video, and I'm going to show it in this video as well, that when you do not have theta step set properly, you get some really ugly pictures. But for this particular picture, we're just going to leave things be. I'm actually going to make theta step equal to 1 and hit graph again. And we see it's the same thing. It's a straight line. It's pretty hard to mess up a straight line. Okay, so we're going to get out of that. Now, let's go back to this. So we took this rectangular, we turned it into polar. Great. Now, what I want to do is graph r equals 4 cosine 3 theta. And when you see r equals 4 cosine 3 theta, this is very, very apparent to me that what we're looking at is a polar equation. Now, real simple, real easy. What I want to do is type r equals 4 cosine 3 theta into my calculator. So it's going to look something like that. R equals 4 cosine 3 theta. And I'm going to graph it on the calculator, and then I'm going to show you how to graph it by hand. Okay? So to graph this on the calculator, and we're going to zoom in just a little bit here. Okay? R equals 4 cosine 3 theta. I'm going to hit graph, and that looks kind of ugly to me. Okay? If you ever get a polar coordinate graph that doesn't look smooth and curved, 99.9% of the time the problem is with your window. So go to your window. And theta is 0 to 2 pi. Theta step is 1 radian. Now, what we're doing is we're starting at 0 and we're making a point. We're going to 1 radian and making a point. We're going to 2 radians and making a point. And we're only getting 6 points. So what if I make this 0.5? We're going to get more points. Let's graph it. Also kind of a jumbled mess. Let's try again. What if I make this 0.1? And now all of a sudden you see a very nice, clean, pretty polar equation. This is a 3-petaled flower. And anytime you have a cosine equation with an odd numbered theta, so cosine 3 theta, cosine 5 theta, cosine 7 theta, you get that number of petals. So whatever this number here is, this 3, whatever that number is, that's how many petals you'll have. And whatever this number here is, this 4, is how long they'll be. So if I zoom in just a little bit more, you'll see that this goes out 4 on the x-axis here. So 1, 2, 3, 4. This goes out 4 steps. And of course these also go 4 steps because they go at an angle. It's hard to tell. So if I were to go back to my equation and change this to, say, 5, press graph again, now the petals go out 1, 2, 3, 4, 5 steps on the x-axis. Okay? And if I change this 3 to a 5, now instead of 3 petals, I get 1, 2, 3, 4, 5 petals. So kind of fun, kind of artistic, something you can do. And one of the things I wanted to do was talk to you about how to graph something like this by hand. Students all the time say to me, well, I understand how to graph this on a calculator, but I really don't know how to graph this by hand. So I want to talk about how to graph this type of thing by hand. And what I want to do is talk about how to graph this thing. You know, if you look at if you look at polar graph paper, and I don't have any polar graph paper, you tend to see an XY axis, and then you tend to see rings. And there's a ring at 1, a ring at 2, a ring at 3, a ring at 4, and then you see these angle lines. Okay, so I've kind of recreated polar graph paper here. And what I've done is I've put a line at 30, at 60, obviously 90 is the y-axis, 120, 150, 180 obviously, and it goes around in increments of 30 degrees, okay? In increments of 30 degrees. Oh my goodness. Which is, you know, pretty simple to do, okay? Now, let me do one thing really quickly, folks. So anyway, now I've got this equation and I want to graph it. Now the only way to graph a polar equation by hand is to sit down and make a table. Okay? Sit down and make a table. Okay? So what I want to do is I want to make a table. And I take my, r equals 4 cosine 3 theta. And here's what we're going to do. Very lightly, I'm going to trace a circle at 1. Okay? And very lightly, I'm going to trace a circle at 2. And this might not make sense to you if you've never done this before, but I'm hoping it's going to make sense to you eventually. So we trace a circle at 3, and we trace a circle at 4. Now, because I've done this before, lucky me, I know that we don't need any more circles than 4. Okay, so I've got my circles and I've got my angle lines, and this is what a piece of polar graph paper would look like, only, obviously neater. And here's what we're going to do. We're going to create a table. Okay, we're going to create a table that's theta and r. Okay, and basically we're going to take this equation and we're going to create well, we're basically going to create this graph here. So anyway, what I want to do, and you'll see that this doesn't come out very well if we do this in increments of 30. But what I want to do is create this table. So I'm going to start theta 0 degrees, 15 degrees, 30 degrees, 45 degrees, 60 degrees, 75 degrees, 90 degrees, 105, 120, and I'm not going to go all the way to 360 because this gets very, very, very tedious. This is the reason you don't want to do these by hand. And if I take this equation and I plug in theta equals 0, okay, well 3 times 0 is 0, the cosine of 0 is 1, and 4 times 1 is 4. So I plot that point. I go out 4 at an angle of 0, and I plot that point. Okay? Now, 15 degrees. Well, if I plug in 15 degrees here, 3 times 15, that's 45. And 4 times the cosine of 45 gives me 2.83. So 2.83. So what I'm going to do is 15 degrees is somewhere between 30 and 0. And 2.83 is very, very close to 3. And so it's going to be a point basically almost 3 from the origin and between 0 and 30 degrees. Okay? Now we're going to plug in 30 degrees. Okay? Well, 3 times 30, right? 3 times 30 is 90. Cosine of 90 is 0. 4 times 0 is 0. So this is 0. So on this 30 degree line, r is 0. And we always go from point 1 to point 2 to point 3. So we go from point 1 to point 2 to point 3. Okay? Now, point 4, 45 degrees. Well, 45 degrees, if you plug that in, 3 times 45, take the cosine of it, multiply it by 4, you get negative 2.83. Well, what does that mean? Well, if you're in quadrant 1, and the radius is positive, you're going to go this way. Well, negative r would be that way. Okay, so what we're going to do is we're going to go on a 45 degree line, which is halfway between 30 and 60. So here's an imaginary 45 degree line, and that 45 degree line goes into both quadrants. And instead of going 2.83 this way, because r is negative, we're going to go 2.83 this way. So we're going to stop just short of the 3 mark there. And that is our third point. And you have to go in the order that you plot these points. 60, so 60 degrees if I plug in 60 degrees here, 3 times 60, take the cosine, multiply by 4, I get negative 4. So what does that mean? On this 60 degree line, we're going to go 4 in that direction because it's negative. So 1, 2, 3, 4. So connect the dots and we go there. And you're starting to see that flower shape come together. 75 degrees is negative 2.83. So I go to 75 degrees. Well, 75 degrees is right here, 75 degrees. And that's also going to go into quadrant 3 there. And the radius I get is negative 2.83. So 2.83 would be this way. So negative 2.83 would be this way, which is going to be 1, 2, not quite 3. And it's going to go there. And so this is going to loop and go there. And then, of course, 90 degrees, we plug that in, we get 0. So the next point would be there. And you're starting to see this flower come together. And if we were to do 105 degrees, that would give us positive 2.83. So at 105 degrees, which is right here, we're going to go out almost 3. And so our last point was at the origin, so we're going to go out from the origin and we're going to hit that. And then at 120 degrees, we get 4, which is going to be here. And so that's going to go that way, right? And then that's going to loop. And the next one's going to be somewhere like here, and it's going to come back here, and it's going to come back here. And then the last ones are going to be, it's going to come this way. And you end up with a 3-petal flower. So very, very, very tedious. And if you graph... if you graph this, you know, in your graphing calculator, you end up with, you know, basically the same picture, but, you know, obviously much prettier. So that's how you graph something by hand in polar coordinates. And I don't recommend it. I mean, that's what technology is for, because this is obviously very tedious and very, very time consuming. And you do need special graph paper to do it unless you want it to look messy like this. But that's kind of the basics of how you do that. And if you have any questions or concerns about this, let me know. It's something that, you know, if you take calculus, you really have to understand polar coordinates, because you do a lot of that in your calculus 3, the third part of your calculus sequence at most universities. So it's something that your instructor would pretty much expect you to know coming in, and would spend very little time reviewing. So can come in very, very handy just to understand how to plot something in polar coordinates, and also how to use your calculator to help you see that picture as well. So if you have any questions, please let me know.